This is matrix of quadratic form. Okay, and the eigenvalues are 1, 1 and minus 2. Okay, 1, 1 and minus 2 are eigenvalues. Now you need corresponding eigenvectors. Okay, so let us start with eigenvector of lambda is equal to 1. Okay, so we know that eigenvector is not a null matrix satisfying the equation A minus lambda I is equals to null matrix. Okay, where A is matrix of quadratic form, lambda is 1, I is identity matrix, and X is column matrix. It cannot be null matrix. Okay, on substituting A 0 1 1 1 0 minus 1 1 minus 1 0 minus 1 into 1 0 0 0 1 0 0 0 1 into X equals to null matrix. Okay, now subtract corresponding elements. It will be minus 1 1 1 1 minus 1 minus 1 1 minus 1 minus 1 into capital X equals to null matrix. Okay, from this stage there are two steps to find eigenvector. One is shortcut method, the other approach is by applying Echelon form procedure. Okay, let us apply Echelon form procedure in order to get the eigenvector. Okay, now apply the operation R2 to R2 plus R1 and R3 to R3 plus R1 so that the coefficient matrix is reduced to Echelon form. Okay, so it will be minus 1 1 1 0 0 0 0 0 0 into capital X equals to null matrix. Now the coefficient matrix is reduced to Echelon form. Now apply back substitution. So back substitution means writing system of equations from the previous matrix representation. So it will be minus x plus y plus z equals to 0. Now you need to consider difference. Difference has two terms. One is number of unknowns. Okay, the other one is rank of coefficient matrix. Okay, unknowns are x, y, z. So number of unknowns are 3 and rank is 1. The difference is 2. So 2 is saying that you need to suppose two unknowns. So let us suppose z and y. Suppose z equals to some k1 and y equals to some k2. Then minus x plus k1 plus k2 equals to 0. Then x equals to k1 plus k2. So the eigenvector is xyz and it is equals to x value k1 plus k2, y value k2 and z value k1. So k1 k2 both cannot be 0. Okay, is the eigenvector of lambda equals to 1. Okay, now let us find the eigenvector of lambda equals to minus 2. Now let us start with eigenvector of lambda equals to minus 2. Okay, so eigenvector is again not a null matrix satisfying the equation A minus lambda I into capital X is equals to null matrix. So A is the given matrix or matrix of quadratic form 0 1 1 1 0 minus 1 1 minus 1 0 lambda is minus 2 I is 1 0 0 0 1 0 0 0 1 into capital X equals to null matrix. Okay, now add or subtract corresponding elements. It will be 0 plus 2 2 1 1 1 0 plus 2 2 minus 1 1 minus 1 2. into x equals to null matrix. Okay. From this step you have two approaches to find eigenvector. Let us apply echelon form method to get eigenvector. Okay. Now interchange the row 1 and row 3. You can interchange with row 2 also. Okay. So it will be 1 minus 1 2, then 1 2 minus 1, last row 2 1 1 into capital X equals to null matrix. Now we are applying echelon form method. So this is possible principal diagonal. You need to make elements below the principal diagonal as zeros. Okay. First let us make the elements along first column below the diagonal as zeros. So for 1, R2 2, R2 minus R1. For 2, R3 2, R3 minus 2 R1. Okay. Now it will be 1 minus 1 2, 0 3 minus 3, 0 1 plus 2 3, 1 minus 4, it is minus 3 into x equals to 0. This is possible diagonal. Still you need to make 3 as 0. The operation is R3 2, R3 minus R2. Okay. Make use of diagonal elements. It will be 1 minus 1 2, 0 3 minus 3, 0 0 0 into x equals to 0. So it is reduced into echelon form. Now apply back substitution. By back substitution, so writing system of equations from the matrix representation, it will be x minus y plus 2z equals to 0 and 3y minus 3z equals to 0. Now you need to consider a difference. It is the difference between number of unknowns and rank of coefficient matrix. Okay. Unknowns are x, y, z. So number of unknowns are 3. Rank is 2. The difference is 1. So this 1 is representing that you need to suppose one unknown so that the other unknowns can be easily evaluated. Now let us continue from this step. Okay. So difference is 1. Difference is 1. It implies that you need to suppose one unknown. I will where eigenvector of minus 2. Okay. I will consider z as some k3. Okay. You can suppose y also. Okay. I have taken z as k3, then 3y minus 3z equals to 0. It implies y equals to z and z value is k3, and we have x minus y plus 2z equals to 0. It implies x minus k3 plus 2k3 is 0. It implies x equals to minus k3. Now the vector is xyz and it is equals to x is minus k3, y is k3 and z is k3 is the eigenvector. Is the eigenvector corresponding to lambda equals to minus 2. Okay. So we have taken matrix of quadratic form A. We have evaluated the eigenvalues. They are 1 1 2, and it is the eigenvector corresponding to 1 and it is the eigenvector corresponding to minus 2. Now let us take some values so that x1 x2 will be more clear. So now let us consider k1 as 1 and k2 as 1. Okay. So I have taken k1 as 1 and k2 as 1. Now it will be 1 plus 1 2 1 1. Okay. So you can take any other numbers so that the eigenvector is not a null matrix. Okay. Let us take k3 also minus 3. It is minus 1 1 1. I have taken k3 as 1. Okay. Now x1 is eigenvector corresponding to 1 it is 2 1 1. Now x2 is eigenvector of the other eigenvalue, that is 1. Okay, it is also 2 1 1. Now x3 is eigenvector of third eigenvalue, that is -2. It is -1 1 1. Okay, so let us name eigenvector corresponding to -2 as x3. Okay, this is eigenvector corresponding to 1, this is eigenvector corresponding to 1, and this is eigenvector corresponding to -2. Okay, so one corresponding eigenvector, the second eigenvalue corresponding eigenvector, third eigenvalue corresponding eigenvector. Okay, so here we are applying the procedure orthogonal reduction, and the important point is these three eigenvectors must be mutually orthogonal. These three eigenvectors must be mutually orthogonal in this particular procedure. Okay, so let us verify x1 and x2. Okay, this is eigenvector corresponding to 1, this is eigenvector corresponding to second eigenvalue 1, this is eigenvector corresponding to third eigenvalue -2. Okay, so in order to check orthogonality condition, okay, the condition is if it is a1 b1 c1 a2 b2 c2 a1 a2 plus b1 b2 plus c1 c2 must be 0. Okay, it is 4 plus 1 plus 1, it is equals to 6, and it is not 0, hence these two are not orthogonal. Okay, x1 and x2 are not orthogonal. Now you check 1 and 3. Now you check 1 and 3. Okay, if it is a1 b1 c1, it is a2 b2 c2, they will be orthogonal if a1 a2 plus b1 b2 plus c1 c2 equals to 0. a1 a2 is -2, b1 b2 is 1, c1 c2 is 1, -2 plus 1 plus 1, it is 0, hence x1 and x3 are orthogonal. Okay, now you take 2 and 3. Now you consider 2 and 3. Okay, if it is a1 b1 c1 a2 b2 c2, okay, then these two will be orthogonal if a1 a2 plus b1 b2 plus c1 c2 is 0. So 2 into -1, it is -2, plus 1 plus 1, it is 0, 0, hence these two are orthogonal. Okay, so in this procedure all the three eigenvectors must be mutually orthogonal, but there is a vector and it is the eigenvalue of 1, it is not orthogonal to other two vectors. Okay, so we have a problem here. There is a vector, there is an eigenvector corresponding to an eigenvalue 1, so that it is not orthogonal to all the other vectors. Okay, so in order to solve this problem, let us assume the first eigenvector as ABC. Okay, there is a problem here. One eigenvector is not orthogonal to remaining eigenvectors. So let us assume x as ABC is the eigenvector of 1 so that it is orthogonal to x1 and x3. Okay, so I have taken ABC as one of the eigenvector of 1, so that it is orthogonal to x1 and x3. If it is x1, then it is x2 and x3. Okay, since x1 is orthogonal to x2, okay, apply the perpendicular condition. It will be a into, this is x2, a into 2, that is 2a, plus b into 1 plus b plus c equals to 0, and x1 is orthogonal to x3. Okay, x1 is orthogonal to x3, then it will be -a plus b plus c equals to 0. Okay, so all the three eigenvectors must be mutually orthogonal, but it is not satisfied here. So we have assumed ABC as the new eigenvector, so that it is orthogonal to other vectors. So let us find ABC. So it is a by something minus b by something c by something. So a by 2 determinant Now close column 1. The remaining coefficients are 1, 1, 1, 1. Now close column 2. Remaining coefficients are 2, 1, minus 1, 1. Now close column 3. Remaining coefficients are 2, 1, minus 1, 1. So it is A by 0, B by 2 plus 1, 3, it is minus 3, C by 2 plus 1, 3. Okay, so the new eigenvector is x equals to 0, minus 3, 3 is the new eigenvector of lambda equals to 1. So you can take 2, 1, 1 as one eigenvector of 1. The other eigenvector of 1 is 0, minus 3, 3. So that all the 3 eigenvectors are mutually orthogonal. The new eigenvectors are x1, x2, x3. Now let us check the orthogonality condition. Okay, 0 into 2, 0, minus 3 into 1, minus 3 plus 3, 0. So x1 and x2 are orthogonal. Now x2 and x3, minus 2 plus 1 plus 1, it is 0. x2 and x3 are orthogonal. Then apply on x1 and x3, it is 0, minus 3 plus 3, it is also 0. Hence all the 3 eigenvectors are mutually orthogonal. And it is the important point in this procedure. These 3 are mutually orthogonal. If any one vector is failed to satisfy the condition, then assume the third vector as ABC and assume that it is orthogonal to the other 2 vectors, so that we will obtain a vector that is orthogonal to all the 2 other vectors. Okay. Now let us form model matrix. Model matrix, let us denote it by P. It will be x1, x2, x3. Okay, it is equals to x1. x1 means first eigenvector, place along the column, first column, 0, minus 3, 3. Then x2, second eigenvector, 2, 1, 1. x3 is minus 1, 1, 1. Okay. Now let us find normalized model matrix. Normalized model matrix. Okay, it can be obtained by dividing with its length. Okay, let us denote it by P cap. It is equals to, take the first column and divide each element in the first column by its length. The length is root over 0 square plus minus 3 square plus 3 square. It is root over 0 plus 9 plus 9. It is root 18. Root 18 is length of this column. Then the new column will be 0 by root 18 minus 3 by root 18, 3 by root 18. Okay, dividing each element of the column by its length. Now take second column, find its length. Length is 4 plus 1 plus 1. It is root 6. It will be 2 by root 6, 1 by root 6, 1 by root 6. Take the last column. Last column length is square root of minus 1 square plus 1 square plus 1 square. It is root 3. Divide each element by its length. It is minus 1 by root 3, 1 by root 3, 1 by root 3. So it is normalized model matrix. It is obtained by dividing each column by its length. Now let us start with the quadratic form. The quadratic form is 2xy plus 2xz minus 2yz. Okay, so we have seen it can be assumed as 1 by 1 square matrix, Okay, the same expression is assumed as 1 by 1 square matrix, and it can be denoted in matrix notation X transpose AX. Okay, where X is a column matrix, column has variables, here the variables are X, Y, Z. A is matrix of quadratic form, A is we have already seen, and capital X is the column matrix. Now you substitute capital X is equals to P cap Y, okay, where capital X is column matrix X, Y, Z, and P cap is normalized model matrix, and Y is column matrix Y1, Y2, Y3. Okay, on substitution you will get the final answer. The final answer is 1 into y1 square plus 1 into y2 square plus minus 2 into y3 square. Okay, it is y1 square plus y2 square minus 2 y3 square. Okay, on simplifying X transpose AX with the help of X equals to P cap Y, we reduce to y1 square plus y2 square minus 2 y3 square. Okay, so you can identify one is the first eigenvalue and one is the other eigenvalue, and minus 2 is the last eigenvalue. So just place eigenvalues as coefficients of the square terms. So after simplification also we will get the same answers. That's why I am writing the answers. Okay, you need to write y1 square, y2 square, y3 square, and the coefficients are just the eigenvalues in the order you evaluated the eigenvectors. So place the coefficients as eigenvalues in the order of calculation of eigenvectors. So this is our required canonical form corresponding to the given quadratic form. Okay, so here it is also asked that you need to write the nature. So nature has several subsections. One is positive definite, negative definite, indefinite, positive semi-definite, negative semi-definite. Here the eigenvalues of matrix of quadratic form are 1, 1, minus 2, in which some are negative and some are positive, hence the nature is indefinite. Okay, so nature is indefinite. The reason is some of the eigenvalues of matrix of quadratic form A are negative and some are positive, hence the nature comes under indefinite. Okay, then we need rank of quadratic form. Okay, so rank of quadratic form is number of non-zero terms in the canonical form. Okay, number of non-zero terms in the canonical form. This is the canonical form. The number of non-zero terms are 3, hence rank is equals to 3. Okay, now you need to identify index. Now let us identify index of quadratic form. So index of quadratic form is number of positive terms in the corresponding canonical form. So it is the number of positive terms in the canonical form. Okay, there are totally 3 terms, out of which the number of positive terms are 2, hence index is 2. And the last one, signature of quadratic form. Okay, so it is the difference between number of positive terms and number of negative terms. Okay, in the canonical form. Okay, here number of positive terms are 2 and number of negative terms are 1, and the difference is 1. So 1 represents the signature. Last one, matrix of linear transformation. Matrix of linear transformation is x equals to p cap y, where x is the column matrix having the variables x, y, z. P cap is normalized model matrix already given, and y is the column matrix. It is y1, y2, y3. Okay, so this is about using a quadratic form into canonical form by using orthogonal reduction. So the important point is eigenvector cannot be a null matrix, and the other important point is all the eigenvectors must be mutually orthogonal. If this condition fails, let us assume eigenvector as ABC and it is orthogonal to two other vectors, so that finally you will obtain three mutually orthogonal vectors. Thank you.